So let's verify our two controllers, and you can do it in MATLAB command window as well, and you can also simulate it in Simulink. So let's do it in Simulink so that you also become familiar with Simulink. Here is blank model. So the transfer function of the system can be implemented using different blocks. Here this block, zero pole block, is more convenient, and let's edit it. There is no finite zero, so let's put 0 over here. Poles of the system, one pole is at -1, the second pole is at s equal to -2, third pole is at s equal to -10, and gain is equal to 1. So we have this system, and then gain, ys over here, there is mistake, so there should be no 0. We put a gain over here, so there which block can be utilized, commonly used blocks, so gain, and gain of 164 to achieve the desired transient characteristics. And then unity feedback, here is the block difference, this one, and reference signal can be step input, is the step input, and can be provided with this block. So step input, and then the actual compared with this one, here should be difference, so let's change it to minus sign, minus, apply. So difference is applied to this system, and then we have unity feedback. So the output can be plotted on a scope. So let's use this scope over here, and the step response of the system. I simulate it for 10 seconds and see the response of the system. So here is the response. These discontinuities are due to larger step size taken by the MATLAB. So let's reduce the step size for numerical simulation so that the curve becomes smooth. Here we can change the step size, model configuration parameters. Here is variable step size, and solver is automatically selected. So additional options. So here the tolerance, let's reduce the tolerance -5, so that the step size, it will take smaller step size to make the curve more smooth. So here we have more smooth curve. We can see that there is a steady state error, and let's say we are satisfied with the transient characteristics, that is, we are happy with the overshoot, rise time, settling time, etc. We want to reduce this steady state error by a factor of 10. For that purpose, we use two different controllers and compare their performance. So let's copy the same figure. So here we augment a controller to the system, and let's use this block. I think this will be again useful, this block. The zeros that we have selected for the first compensator, there was 0 at -0.111, and the pole was at 0.01. Gain is approximately 1. So we have selected this controller. Let's plot it on the same graph so that we can see their comparison. Here we have multiplexer, commonly used blocks. So multiplexer, which will multiplex these two signals and plot it on the same graph. So here and here. So let's see their performance. Here we have designed a compensator, and we can see that this blue curve, which is the response for the compensated system, is transient characteristics are almost the same. There is some distortion. However, the steady state error is reduced. That is reduced by a factor of 10. We can simulate it for larger times. That will be more obvious. For 20 seconds, you see that the steady state error is significantly reduced. Let's now try the second compensator. Second compensator, poles were placed at there was 0 was placed at 0.011 and pole was at 0.001. So we have this second compensator. Let's see its performance. Again, let's plot it on the same graph. So we increase the number of signals to 3, and here is the third signal. So this is the second compensator. You see that this orange line, which is the response of compensated system with the second compensator, almost overlaps with the yellow curve, which is the response of the actual system. So transient characteristics, the second compensator has less distortion on the transient characteristics. However, the steady state error, there is a long tail. It will finally approach to same value, but it will take more time. So let's plot it for more time, 100 seconds. You see that it is gradually reaching to the same value as this blue curve, which is the response of system with the first compensator. However, there is long tail in the response of the system. So which compensator among the two you will prefer, that depends upon your preferences. That is whether you can afford such long tail in the response or not, or whether you can afford distortion in the transient characteristics or not.